Today we prove the fundamental theorem of finite abelian groups uniqueness part. In the previous module we proved fundamental theorem of finite abelian groups existence part, where we proved that every finite abelian group is a direct sum of cyclic groups of order of the form p to the power n, that is a power of some prime. And then we introduced elementary divisors of a finite abelian groups. In the uniqueness part of the fundamental theorem of finite abelian groups, we proved that two finite abelian groups G and H are isomorphic if and only if they have the same elementary divisors. This result can be applied to find non-isomorphic finite abelian groups of a given order. And recall that we have Zm direct sum Zn is isomorphic to Zmn if GCD Mn equal to 1. With the help of this result, we will introduce a new notion, namely invariant factors of a finite abelian groups. Also we prove that two groups are isomorphic if and only if they have the same invariant factors. Let us first recall the definition of elementary divisors. Let G be a p primary abelian group if G is the direct sum of the primary cyclic groups G1, G2, Gr, where order of Gi is equal to p to the power ni and p to the power n1 less than equal to p to the power n2, which is less than equal to and so on less than equal to p to the power nk, then p to the power n1, p to the power n2 and so on p to the power nk are called the elementary divisors of G. In case G is a finite abelian group having order p1 to the power n1, p2 to the power n2 and so on pk to the power nk, where the primes p1, p2, pk are arranged in the ascending order, then the collection of the elementary divisors of the p primary components gp1, gp2, gpk are called the elementary divisors of G. Also recall that if a p primary abelian group G has elementary divisors p to the power n1, p to the power n2 up to p to the power nk, then G is isomorphic to the direct sum of the cyclic groups Z p to the power n1, Z p to the power n2 and so on Z p to the power nk. Now let us come into the main theorem, that is the fundamental theorem of finite abelian groups. The statement is two finite abelian groups G and H are isomorphic if and only if they have the same elementary divisors. First, suppose that two abelian groups G and H have the same elementary divisors, and also assume that p to the power n1 less than equal to p to the power n2 less than equal to and so on less than equal to p to the power nk are the elementary divisors of G and H corresponding to a prime p dividing order G is equal to order H. Then the p primary component of G is Gp, which is isomorphic to Z p to the power n1 direct sum Z p to the power n2 direct sum so on direct sum Z p to the power nk, and of H is HP, which is isomorphic to Zp to the power n1 direct sum Zp to the power n2 direct sum so on direct sum Zp to the power nk. In a word, both Gp and Hp are isomorphic to a same group, and hence it follows that Gp is also isomorphic to Hp. Thus, the p primary components of both G and H are isomorphic, and this is true for every prime p, and hence it follows that G is isomorphic to H by the primary decomposition theorem. Conversely, assume that the groups G and H are isomorphic. Then, by the primary decomposition theorem, Gp is isomorphic to Hp for every primary divisor p of order G is equal to order H. Assume that the p primary component Gp is isomorphic to Zp to the power n1 direct sum Zp to the power n2 direct sum so on direct sum Zp to the power nr, and Hp is isomorphic to Zp to the power m1 direct sum Zp to the power m2 direct sum so on direct sum Zp to the power ms. Since Gp and Hp are isomorphic, assume that f Gp to Hp is an isomorphism. Then it follows that since f is an isomorphism, so image of a cyclic subgroup under F is also cyclic. Thus, f of Z p to the power ni is a cyclic subgroup of Hp, and order of fz p to the power ni is same as the order of Z p to the power ni, that is p to the power ni, and we have Hp is equal to f z p to the power n1 direct sum f z p to the power n2 direct sum so on direct sum f z p to the power nr. Since both Gp and Hp are p primary abelian groups, so it follows that R equal to S and p to the power ni is equal to p to the power mi for every 1 less than equal to I less than equal to R. Therefore, G and H have the same elementary divisors. As an application of the fundamental theorem of arithmetic, we have the following important conclusion. Suppose that G is a direct sum of two subgroups AB and H is a direct sum of two subgroups CD. If G and H are isomorphic and the subgroups B is isomorphic to the subgroup D, then the subgroup A must be isomorphic to C. This is a very important result in respect of its application. The fundamental theorem of finite abelian groups can be used to determine non-isomorphic abelian groups of a given order. Recall the statement of the theorem. Two finite abelian groups G and H are isomorphic if and only if they have the same elementary divisors. Since elementary divisors depends only on the order of the group and all possible sets of elementary divisors can be determined just from the order of a group. So, analyzing the order of a finite abelian group, it is possible to find total number of non-isomorphic abelian groups of a given finite order. Let n be a positive integer. By a partition of n, we mean a k tuple n1, n2 up to nk of positive integers such that their sum is n. Also, we assume that n1, n2, nk are arranged in ascending order. For example, the partitions of the positive integer 5 are 5, 1 plus 4, 2 plus 3, 1 plus 1 plus 3, 1 plus 2 plus 2, 1 plus 1 plus 1 plus 2 and sum of 5 ones. Suppose that G is a p primary abelian group and order G is equal to p to the power n. If p to the power n1, p to the power n2 up to p to the power nk are the elementary divisors of G, then we have G is isomorphic to the sum of the cyclic groups Z p to the power n1, Z p to the power n2 plus so on plus Z p to the power nk. So, the order of the group on the right hand side is p to the power n1 plus n2 plus so on plus nk, whereas of the left hand side, that is of G, is p to the power n, and so n is the sum of n1, n2, nk. Thus, every set p to the power n1, p to the power n2 so on p to the power nk of elementary divisors of a p primary abelian group of order p to the power n is associated with a partition n1, n2 up to nk of n. Now, we show that conversely, every partition of n yields a set of elementary divisors of a group of order p to the power n. Suppose n1, n2, nk is a partition of n. Then we have unique up to isomorphism abelian group Z p to the power n1 direct sum Z p to the power n2 direct sum so on direct sum Z p to the power nk, and order of this group is p to the power n since n1, n2, nk is a partition of n. Thus, it follows that total number of non-isomorphic abelian groups of order p to the power n is equal to the number of partitions of n. For example, we show that given any prime p, there are exactly 3 non-isomorphic abelian groups of order p cube. Note that there are only 3 partitions of 3, namely 3, 1 plus 2, 1 plus 1 plus 1. The partition 3 corresponds to the group Zp cube, and the partition 1 plus 2 corresponds to the group Zp direct sum Zp square, and similarly the partition 1 plus 1 plus 1 corresponds to the group Zp plus Zp plus Zp. Note that the group Zp plus Zp square has no element of order p cube. So, the first group cannot be isomorphic to the second group. Similarly, it can be shown that no 2 of these 3 groups are isomorphic. Now, we will prove a different formulation for representing a finite abelian group as a direct sum of cyclic subgroups. And to do this, we will use the result that the product of Zm and Zn is isomorphic to Zmn if and only if the integers m and n are relatively prime. So, using a direct sum decomposition of a finite abelian group as sum of cyclic subgroups, we can rearrange the components or decompose the components and again compose in such a way that the orders of the cyclic subgroups will be placed in an ascending order with more specialities. Now we prove that every finite abelian group G can be represented as a direct sum of the cyclic groups C1, C2, Ct of order M1, M2, Mt respectively, such that M1 divides M2 divides and so on divides Mt. Let order G be equal to P1 to the power N1 into P2 to the power N2 and so on into Pk to the power Nk. Then by the primary decomposition theorem, G can be represented as a direct sum of P primary components Gp1, Gp2, Gpk. Also, we have by the basis theorem for every Pi, Gpi is a direct sum of the cyclic groups Zp1 to the power Ni1, Zpi to the power Ni2 and so on Zpi to the power Nit. Also we assume that Ni1 is less than equal to Ni2, less than equal to and so on less than equal to Nit. Let us consider some dummy exponents Nij equal to 0 so that the same index t can be used for all I equal to 1, 2 up to k. This is just make the presentations simple. Define Mj to be the product of jth elementary divisors of the primary components Gp1, Gp2 up to Gpk. Thus, Mj is equal to P1 to the power N1j into P2 to the power N2j and so on Pk to the power Nkj. And since the elementary divisors are arranged in an ascending order, we have M1 divides M2 divides M3 and so on divides Mt. And also we have Zp1 to the power N1j direct sum Zp2 to the power N2j and so on plus Zpk to the power Nkj is isomorphic to Zmj by the result that Zm direct sum Zn is isomorphic to Zmn when Mn are relatively prime. We denote Zmj, the cyclic group Zmj by Cj, and hence it follows that G is equal to the direct sum of the cyclic groups C1, C2, Ct, where order of C1 divides order of C2, which divides order of C3 and so on divides order Ct. Let G be a finite abelian group if G equal to the direct sum of the cyclic groups C1, C2, Ct satisfying the condition that M1 divides M2 divides so on divides Mt, where Mi is the order of the cyclic group Ci, then M1, M2, Mt are called invariant factors of G. Now I give some examples how to find invariant factors of a given finite abelian group. Suppose we are given a finite abelian group Z2 plus Z4 plus Z3 plus Z3. Our problem is to rearrange the cyclic groups and combine in such a way that order of the first component divides the order of the second and so on. Note that here the two primary component is Z2 plus Z4 and the elementary divisor of G2 is 2, 4. And similarly, the elementary divisors of G3 are 3, 3. So, according to the previous proof, we will multiply 2 and 3 and 4 and 3. And we can do this because Z2 direct sum Z3 is isomorphic to Z6 and Z4 direct sum Z3 is isomorphic to Z12. Thus, the group can be represented as Z6 direct sum Z12, where 6 divides 12. Thus, the invariant factors are 6, 12. Whereas, for the group Z8 plus Z3 plus Z3, the elementary divisor corresponding to the primary component G2 is only 8. But for G3, we have two elementary divisors 3, 3. Since G2 has only one elementary divisor, whereas G3 has two elementary divisors, hence we have to introduce here a dummy elementary divisor 1 to the G2, and then we get the rearranged elementary divisors with the dummy is 1, 8, 3, 3, and we get the invariant factors as 1 into 3 and 8 into 3. Thus, the representation of Z8 plus Z3 plus Z3 is Z3 plus Z24 and the invariant factors are 3 and 24. You must note that in case of the group Z4 plus Z9, since 4 and 9 are relatively prime, it can be rewritten as Z36 and the invariant factor will be just 36. Now, it is a question whether invariant factors are unique. To answer this, we prove two finite abelian groups G and H are isomorphic if and only if they have the same invariant factors. Let G and H are two isomorphic groups. Suppose that G is equal to C1 plus C2 plus so on plus Ck, where Ci is a cyclic group of order Mi and M1 divides M2 divides so on divides Mk, and assume that H is equal to D1 plus D2 plus DL, satisfying the similar condition. Since Ck is a cyclic group of order Mk, so Ck and hence G has an element of order Mk. Also we have Mi divides Mk for all I, and this implies that Mkg equal to 0 for all G belongs to G. Therefore, the exponent of G is Mk. Similarly, the exponent of H is NL. Since G and H are isomorphic, so the exponents Mk and NL are identical. Thus, Ck and DL are two cyclic groups of the same order, and so Ck is isomorphic to dl. Then it follows that C1 direct sum C2 direct sum up to direct sum Ck minus 1 is isomorphic to D1 direct sum D2 direct sum so on direct sum dl minus 1. Then by the induction hypothesis, k minus 1 is equal to l minus 1 and Ci is isomorphic to di for every 1 less than equal to I less than equal to k minus 1. For the converse, assume that G and H are two groups having the same invariant factors. Then G is equal to C1 direct sum C2 direct sum Ck and H is equal to D1 plus D2 plus so on plus Dk, where Ci and Dj are cyclic groups such that order of Ci is equal to order Di. Since Ci and Di are cyclic groups having same order, it follows that Ci is isomorphic to Di for every I, and hence C1 direct sum C2 and so on direct sum Ck is isomorphic to D1 direct sum D2 direct sum so on direct sum Dk, that is G is isomorphic to H. Now, if we are given invariant factors, how the elementary divisors can be found? Suppose Z6 plus Z12 is a finite abelian group we are given. Then from 6 divides 12, we get 2 into 3 divides 2 square into 3. In other words, we will separate or rewrite Z6 according to the prime factors. So Z6 can be rewritten as Z2 direct sum Z3, whereas Z12 can be rewritten as Z4 direct sum Z3. Thus, the elementary divisors corresponding to the two primary components are 2 and 4, whereas the elementary divisors corresponding to the three primary components are 3, 3. So, the elementary divisors of this group is 2, 4, 3, 3. Similar for Z3 plus Z24, we have the elementary divisors 8, 3, 3, because Z24 can be decomposed as 2 cube into 3. In case of Z36, 36 has the unique factorization as 2 square into 3 square. So, 2 square will give us the elementary divisor corresponding to the two primary component, whereas 9 is the, that is 3 square is the elementary divisor corresponding to the three primary component. Thus, 4, 9 are the elementary divisors of Z36. I will conclude this module with this example. In this example, we will find all possible non-isomorphic abelian groups of order 5 square into 7 cube. Here, the order of the group has two prime divisors, namely 5 and 7. 5 has power 2 and 7 has power 3. So, we are to consider number of partitions of 2 and number of partitions of 3. Note that there are only 2 partitions of 2 and 3 partitions of 3. We show that there are exactly 2 into 3, that is 6 non-isomorphic abelian groups of order 5 square into 7 cube. The first group is corresponding to the partition 2 of 2 and 3 of 3. In this case, the elementary divisors are 5 square and 7 cube, and so the group will be Z5 square direct sum Z7 cube. Corresponding to the partition 2 of 2 and 1 plus 2 of 3, we have elementary divisors 5 square, 7, 7 square, and the group is Z5 square plus Z7 plus Z7 square, and similarly for others. Thus, since it depends on the number of partitions of 2 and number of partitions of 3, so the total number of ways for getting non-isomorphic abelian groups of order 5 square into 7 cube is 2 times 3 is equal to 6. Thus, we see that external direct product and internal direct product are the techniques to represent finite abelian groups. With the help of primary decomposition theorem, basis theorem, and fundamental theorem for finite abelian groups, now it is possible to get total number of non-isomorphic abelian groups of a given order, and also we can represent all possible abelian groups of a given order up to isomorphism. In the next chapter, we will consider the non-abelian case.